Welcome back for another day of math in Math 8. We are in Unit 2, Lesson 7, taking a deeper look at similarity. Specifically today, we're talking about similar polygons, and what we're going to really look at is the sides and the angles of similar polygons to determine are these polygons similar or not. To start out, we have three questions here. We're going to choose whether each statement is true in all cases, some cases, or no cases. Go ahead and take a minute to answer those questions. All right, now that you're back looking at these things, let's go ahead and break these down to talk about why or why not these are true. In the first one, it says two figures are congruent, then they are similar. So here's the key words here: congruent, being similar. So what we're saying in this case is it would be a true statement if all congruent figures could be considered similar. In this case, this is in all cases, this is true. And the reason for that, if you think about congruence is proven by transformation. So rotation, translation, and reflection. When we talk about similar figures, they are proven by the same three rigid transformations, but then we add in dilation. Dilation doesn't always change the size of a shape, especially if it's by a scale factor of 1. So when we look at this, congruent figures can be taken from one another by using the rigid transformation. Similar figures use these same transformations, but they also use dilation. If we don't do a dilation, the figures still stay similar because they meet the criteria of the side lengths being proportional to each other, in this case equal, and the angle measures be equal. When we have two figures that are similar, then they are congruent. Well, this one doesn't work the same way, because not all similar figures are congruent. Under similarity, again, we go back to the dilation piece. While similarity and congruent use both transformations and dilation, congruent, if we dilate anything by a scale factor other than 1, we don't have the same size figure anymore. We now have a proportional figure. So this one's only in some cases. And finally, number 3, if an angle is dilated with a center of dilation at its vertex, the angle measure can change. Seeing that word right there, seeing those words may change, that's an automatic disqualification for having truth, because under dilation, we still use rigid transformation, which means angle measures are preserved. Angle measures can't change. Lengths of segments can change, but only proportionally. So there are no cases where this will ever be true. Looking at the next set, are they similar? We're going to be talking about, in the next two problems, talking about a couple of kids that have their point of view on these different pieces. Let's say you take a square and a rhombus, and Priya and Claire are looking at the same two figures. Priya says these polygons are similar. So she's saying similar because their side lengths are all the same. So she's only looking at the side lengths, which she's right, the side lengths are all the same. Claire says these polygons are not similar because the angles are different. So here's Priya's point of view, is talking about side lengths are the same. Claire says angles are different. Do you agree with either Priya or Claire, or neither one, or both? Explain your reasoning real quick. Right, welcome back. Here's the key things that we want to look at. Under similarity, remember that side lengths have to be proportional, if not equal, but angles must be equal, because every single similarity, every single congruence relates back to rigid transformation. And so under rigid transformation, angle measures must be kept the same. So in this case, what we need to do is we need to agree with Claire because under similarity, angle measures must be equal. Must be equal due to rigid transformation. Okay, without rigid transformation, we don't even have similarity or congruence. So we have to keep angle measures the same. The next one. Here's two rectangles. Under these rectangles, there's a question that says, or here's the two student statements. Jada says these rectangles are similar. So she's making the claim they are similar because the side lengths differ by 2. Lynn says these rectangles are similar. I can dilate AD right here, so this side, and BC, okay, so this side and this side, by a scale factor of 2. And then she says she can take the other sides, AB and CD, using a scale factor of 1.5 to make the rectangles congruent. Then I can use translation to line up the rectangles. Do you agree with either Jada or Lynn, or neither one, or both of them? Explain your reasoning. All right, let's take a look at what they said again. Jada said that the side lengths differ by 2. When we talk about differ in math, that means that we're using subtraction. Subtraction doesn't work under similarity because under dilation, we have to use a scale factor, which means we have to multiply. We cannot subtract under a dilation, so Jada is incorrect. When we look at Lynn, Lynn is using two different scale factors, 2 and 1.5. Under dilation, you cannot use two different scale factors because that's not keeping the shape proportional. It's growing and shrinking at two different rates, which we can't do. So do you agree with Jada or Lynn? We should have said neither for the following reasons that I talked about. We have to use a scale factor, which means we have to multiply. And Lynn, we can't follow her advice because we can't use more than one scale factor in our work. Otherwise, we don't have proportionality. So, are you ready for some more? Take a look here, polygons A through H. So all of these different measures here, we're comparing these two figures to each other, and we're saying that all of the following are rectangles, giving these shapes right here, GHBA, FCED, and then all the other ones that are here. Which is greater? The area of the blue rectangle, this one is blue. I know you don't have the color, so I'm just telling you this one's blue, and then these ones are yellow. Give it a try. Give me some reasoning, and let me know what you think for a little bit of a bonus here. I want to see what you can come up with. Here's one more with the same requirements. On the left, we're skipping over 7-3, by the way. On the left is an equilateral triangle where the dashed lines have been added, showing that you can partition an equilateral triangle into smaller similar triangles. So this has been broken up into triangles that are of equal value or equal side lengths, equal angles. So these little triangles are exactly the same shape as the larger equilateral, but it's broken down into 4 triangles. Find a way to do that exact same thing with the one on the right. Keep in mind that the shape has to be exactly the same. So if your first thought was, oh, we'll just cut it into 3 squares because those are all the same, is that shape a square? Since it's not, you can't do that. So I do want you to use that idea of the squares that you did there to kind of get you started, but there is a way to go ahead and take this shape and break it down into smaller pieces and have the exact same original shape. I'd love to see your drawing and your picture. Please give that a chance and plug it in right here. And that takes us to the end. Here's what we've learned from this lesson. When two polygons are similar, there are 3 major criteria we have to account for. First off, every angle and side in one polygon has to have corresponding parts in the other polygon, meaning that they have to look the same. Otherwise, there's no correspondence. All the pairs, and I mean all pairs of corresponding angles have the same measure. That is a non-negotiable. The angle measures must be preserved from one shape to the next shape, meaning they must be kept the same. Corresponding sides, they have to be related by a single scale factor. Otherwise, we don't have proportionality. Each side in one figure is multiplied by the scale factor to get the corresponding side length of the other figure. And again, without using just one scale factor, we lose proportionality, meaning that the figures don't grow and shrink the same way. Kind of like if you were zooming in and out on a picture on a phone or a computer, you have to see that growth has to occur at the same rate all the way through. Here's two rectangles that are shown below, and the question is, are they similar? Well, let's look at our criteria above. Is every single angle in this rectangle the same as this rectangle? Well, sure, because they're all 90-degree angles. So right now we've met criteria 1. The second piece, or I guess I skipped that one. Yeah, all these angles are the same, but now let's look at the corresponding sides. Are they related by a single scale factor? Well, let's say that this rectangle is a dilation of this rectangle, meaning it's made smaller. Under the rules of dilation, to be able to figure out the scale factor, we want to take the dilated image and divide it by the original figure. So we would take 3/4, and then we would compare that to a ratio that compares the smaller side to the larger side again of 2/3. And then we have to look at those two ratios and decide, are they equal or not? Well, we know that 3/4 and 2/3 are certainly not equal. Even if we checked it against the other way of going from small to large, all we would see different is 4/3 compared to 3/2, which we know again is not equal. It looks like the rectangles could be similar if you match the long edges, match the short edges as corresponding points. All the corresponding angles are congruent because they're all right angles, but calculating the scale factor on what we think it looks like isn't good enough to make similarity. We have to understand that the scale factor has to be consistent all the way across, all the way around for all the parts. So these rectangles are not similar because the scale factor for all the parts must be the same. Finally, we look at two other figures here. Here's an example that shows how sides can correspond, in this case with a scale factor of 1 because the side lengths haven't changed. But in these quadrilaterals, they are not similar because the angle measures are not equal to the angle measures in the other figure. So keep that in mind. Make sure you understand these three pieces, that you remember those three pieces. We must have equal angle measures to be able to consider to be similar, and we must have proportional growth by a single scale factor for all polygons. Thanks for your work today. Make sure you keep doing make sure you do your homework tonight, following for the same lesson. I'm really appreciating what you're doing for your work. Keep working hard and don't you dare give up. Have a great day.